Determining the structure-property relation is a crucial task in various scientific disciplines, including materials science, chemistry, biology, and physics. This relation refers to the connection between the spatial distribution of substances or materials and the resulting properties that depend on these spatial details. Traditionally, forward simulation models have been employed to understand and predict this relation. Recently, machine learning algorithms have been applied to enhance and accelerate simulation models or as surrogate models. In this work, 6 machine learning techniques are developed and investigated using 2 datasets from materials science. Data from a 2-dimensional Ising model for predicting the formation of magnetic domains and data representing the evolution of dual-phase microstructures from the Cahn-Hilliard model. The accuracy and robustness of these models are analyzed, and the reasons for their performance differences are elucidated. The impact of incorporating domain knowledge through tailored features is studied, and general recommendations are derived based on the availability and quality of training data. The 6 machine learning techniques employed include convolutional neural networks and support vector regression, which are used to predict microstructure properties. The performance of these models is evaluated using metrics such as power spectrum density, which characterizes the spatial distribution of materials. The use of machine learning algorithms as surrogate models has the potential to accelerate materials science simulations, enabling the rapid exploration of complex structure-property relations. The developed models can be applied to a wide range of materials science problems, providing a promising avenue for advancing the field. The study of the microstructure properties relation is a crucial task in various scientific fields, including meteorology, materials science, and biological systems, across different length scales. Mathematically, this involves finding the mapping from a spatial distribution of values to a single scalar, vectorial, or tensorial value. For instance, in geological measurements, the 3-dimensional structural details of the Earth's crust are linked to displacement measurements, which represent an effective property. Similarly, in weather forecasting, spatial details such as cloud structure and airflow streamlines determine properties like cloud top temperature and particle effective radius. In materials science, microstructure refers to phenomena that occur on a small scale, disturbing the perfect crystal lattice, and giving rise to properties like hardening behavior in alloys or increased strength with decreased grain size. To predict such properties, dedicated simulation models have been developed, including density functional theory calculations and molecular dynamics simulations, which can accurately calculate structures and properties on a microscopic scale. However, these methods are computationally expensive and often limited by numerical instabilities. Recently, statistical machine learning and deep learning algorithms have emerged as potential surrogate models or alternatives for predicting the structure-property relation, overcoming the limitations of classical methods in terms of computational cost and robustness. For example, deep learning approaches have been applied to weather forecasting to predict weather conditions based on atmospheric and oceanic properties. These machine learning and deep learning algorithms have the potential to revolutionize the study of microstructure properties relations across various scientific fields. Machine learning techniques have been successfully applied to various fields, including remote sensing for short-term earthquake forecasting, outperforming conventional approaches. In earthquake forecasting, data augmentation using discrete waveform transforms and singular value decomposition increases the variety of earthquake data for training machine learning models. These models can predict the response of nonlinear systems for unseen earthquakes or replicate nonlinear finite element model predictions. In computational biology, machine learning has been used for protein structure prediction, predicting melting temperatures, and identifying ligand binding sites. In materials science, machine learning has been employed for surrogate modeling, encoding material properties into microstructure images, and solving the inverse design problem. Examples include predicting hardness, relative mass density, diffusivity, permeability, and effective heat conductivity based on microstructural texture variance, pore space geometry, and other material properties. Researchers have incorporated physics knowledge into models, such as physics-guided convolutional neural networks and physics-informed multi-LSTM networks, to improve surrogate modeling for structural response prediction. Physics-informed neural networks have been used to solve nonlinear partial differential equations, and elastoplastic neural networks have been developed to replace conventional yield functions, plastic potential, and plastic flow rules. Despite the success of machine learning in various domains, systematic studies on training behavior, generalizability, and performance with varying data amounts are rare. This knowledge gap makes it challenging to compare and estimate model reusability for different problem classes. This study investigates the benefits and drawbacks of various machine learning approaches for predicting properties from structures of two materials science datasets, differing in complexity and incorporating domain knowledge through feature engineering. The datasets, obtained from materials scientific simulations, cover two extremes: the self-organized magnetization of a domain, relating spatial magnetization structure to temperature, and another dataset with distinct characteristics. Machine learning models are applied to predict the evolution of microstructures in materials science, a critical problem in physics and engineering. Two datasets are investigated, representing different types of microstructures, one based on stochastic processes and another obtained from the solution of coupled partial differential equations. These datasets, visualized in Figure 1, showcase the final state of magnetization at various temperatures and the evolution of energy and microstructure over time. 5 machine learning approaches are explored to predict the scalar property associated with the given microstructure images. These include a piecewise constant regression model with simple features as a baseline, a support vector regression model with physics-based features, a convolutional neural network approach utilizing Fourier and wavelet transformations, a combination of a pre-trained ResNet and principal component analysis for input features, and several, off-the-shelf, CNNs with different pre-training types. The datasets are generated using materials scientific simulations, covering two extremes: stochastic processes and smooth, continuous processes described by partial differential equations. The underlying theory and implementation of these simulation models are detailed in the paper's appendix. This work contributes to the development of novel machine learning methods that can effectively predict the evolution of microstructures, crucial for understanding and optimizing material properties in various applications. The Ising and Cahn-Hilliard datasets are two microstructure datasets used to study phase transitions and magnetic properties. The Ising dataset consists of 50,000 images, each representing different magnetic spin directions at various temperatures, with a uniform distribution of temperature values, resulting in a balanced training dataset. The two-dimensional microstructure displays the magnetization of a domain with two different magnetic spin directions, indicated by black and white colors. The evolution of the system is determined by a Metropolis Monte Carlo algorithm, where each simulation starts with a random distribution of spin values and evolves for a number of steps. The final microstructure is saved as a black and white image, where black represents a negative spin and white represents a positive spin. The microstructures change significantly with temperature, transitioning from random to ordered states below the critical temperature Tc approximately equals 2.269 in non-dimensional units. Figure 1a shows example images at 3 different stages, labeled as A, B, and C, with corresponding temperature values of 11, 102, and 222, respectively. In contrast, the Cahn-Hilliard dataset represents the microstructure of a two-phase alloy system, governed by a set of coupled partial differential equations. This system is more complex than the Ising model due to the larger number of physical phenomena considered. Each image represents the microstructure corresponding to the system's energy, with values ranging from 589 to 7054 J/μm³. The simulation exhibits two parts: a rapid energy decay followed by a slower decay. To reduce computing time, a non-constant time stepping with exponentially increasing time steps is used. The dataset consists of 20 simulations performed with random initial microstructures and values between 0 and 1. Histograms of the training data distribution for both datasets are presented in Figure 2. The Ising dataset has a mainly uniform distribution, resulting in a balanced training dataset, while the Cahn-Hilliard dataset shows a non-uniform distribution, indicating a potential challenge in achieving balanced training. The dataset for this study is generated using a molecular dynamics simulation, consisting of two parts. The first part involves an initial 2000 steps with increasing time steps, where microstructure data is stored at every step. The second part consists of a subsequent 10,000 steps with a constant step size, where image data is exported at every 10th step. This results in a dataset of approximately 60,000 images. The energy values of the dataset exhibit a strong imbalance, with significantly more data in the low-energy regime, similar to real-world datasets. This imbalance is a characteristic of regression-type problems, where the goal is to predict properties from microstructures. To address this problem, a range of statistical and deep learning methods are considered. A baseline is established using simple statistical learning methods with basic features, followed by statistical learning methods with appropriate features, and deep learning approaches that do not require sophisticated features but may require larger training datasets. Three types of features are used to represent the images: a minimalistic, domain-agnostic feature, and two physics-based features of varying complexity. The minimalistic feature, denoted as grad, is a simple gradient-based feature that does not require domain knowledge. It is calculated as the average gradient magnitude of the image array, approximated using a central finite difference scheme. This feature can be easily applied to other datasets and does not require further domain-specific knowledge. The grad feature is defined as x equals 1, n dot operator m, n array summation, I, j, u, I, j, where u, I, j, is the pixel value, and m and n are the number of rows and columns, respectively. This feature is used as a baseline to evaluate the performance of more complex features and methods. In microstructure image analysis, physics-based feature engineering is applied using the power spectral density, PSD, to capture characteristics of wavelength distributions. This approach is motivated by the periodic boundary conditions and phase transitions observed in datasets from the Ising and Cahn-Hilliard models. The PSD is derived through Fourier transformations, radial averaging, and extraction of Fourier amplitudes, making it translation invariant in 90-degree rotation and flipping invariant. Figure 3 presents PSDs for three microstructures from both datasets, showing significant power in features with wave numbers less than or equal to 3. Indicating patterns at least one-third of the image size. The PSDs exhibit a roughly linear behavior in double logarithmic plots, enabling differentiation between microstructures at different temperatures and energy values. The slope and intercept of the fitted lines, after back transformation from the double logarithmic scale, serve as features to characterize each microstructure image. Figure 4 displays the temperature and energy as a function of these two features for each training dataset. While the points are clearly localized, the features of the dataset also contain significant scatter. Notably, the Cahn-Hilliard dataset shows an unexpected drop at an energy value of approximately 1200 J per cubic micrometer, attributed to poor data representation in this region. The two features describing the microstructure through the approximated PSD are denoted as phys feet 1 inch throughout the remainder of the work. These physics-based features provide a robust means of characterizing microstructure images, allowing for differentiation between microstructures at different temperatures and energy values. Figure 3 presents the microstructure and corresponding power spectral density, PSD, plots for the Ising and Cahn-Hilliard datasets. The PSD plots are displayed on a double logarithmic scale, where k represents the wave number and p, k, denotes the normalized power. A linear fit is applied to the PSD plots, yielding intercept and slope values after back transformation to the linear scale. To overcome the information loss resulting from strong dimensionality reduction in previous features, the feature engineering pipeline for extended physics-based features, denoted as phys feet 2, is introduced. This approach considers the entire PSD curve, rather than just a linear fit, and incorporates additional features that capture new aspects. One such feature is the gradient of the image, u, I, j, calculated using equation 2. The PSD of the original image and the gradient image are computed, resulting in two unidimensional arrays of 32 values each. These arrays are stacked to form a 2 times 32 array, which is then normalized using logarithmic scaling to avoid numerical errors due to high PSD values. The normalized PSD is calculated using equation 3. The final set of features, referred to as CNNPCA, combines image embedding with dimensionality reduction to achieve high accuracy without relying on domain knowledge and enable fast and computationally cheap regression models. The CNNPCA features are obtained by performing image embedding, followed by dimensionality reduction using principal component analysis, PCA. In the realm of material science research, visualizing and engineering features from complex datasets is a crucial step in understanding the relationship between scalar features and investigated properties. This page delves into the visualization and feature engineering pipeline for both the Ising and Cahn-Hilliard datasets, providing insights into their intricate patterns and correlations. Figure 4 illustrates the relationship between two scalar features and the investigated property, with the top row focusing on the Ising dataset and the bottom row on the Cahn-Hilliard dataset. The blue data points are rendered translucent to provide clarity in the data distributions. The middle and right columns of Figure 4 showcase projections of the feature space and fitted curves, representing the model response. These visualizations enable researchers to identify patterns and correlations between the features and the target property, which are critical in capturing underlying physical phenomena. The power spectral density (PSD)-based feature engineering pipeline, as depicted in Figure 5, plays a pivotal role in capturing the complex patterns present in the considered type of data. This pipeline consists of several stages: input image preparation, dimensionality reduction in scaling, concatenation, and logarithmic normalization. The original image and gradient magnitude images are initially processed, followed by dimensionality reduction and scaling to obtain 64 by 64 by 2 and 32 by 64 by 64 features, respectively. These features are then concatenated and subjected to logarithmic normalization, resulting in the final 2 by 32 PSD features. The significance of this pipeline lies in its ability to distill complex patterns from the input images and convert them into meaningful scalar features that can be effectively utilized by machine learning models. By leveraging the PSD-BASED feature engineering pipeline, researchers aim to enhance the accuracy and robustness of their models in predicting the investigated property. This approach not only facilitates a deeper understanding of the datasets but also opens up new avenues for further exploration and analysis in the field of material science. The CNNPCA-SVR model, visualized in Figure 6a, combines a convolutional neural network, CNN, with principal component analysis, PCA, and support vector regression, SVR. Specifically, a pre-trained ResNet-18 with ImageNet weights is used for image embedding without fine-tuning, generating a 512-element vector of temporary features from the average pooling layer. These features are then reduced in dimensionality through PCA, and the resulting principal components serve as inputs for the SVR model. The visualization of the first two principal components of the ResNet-18 weights for the Ising and Cahn-Hilliard datasets is shown in Figures 6b and 6c, respectively. The Ising dataset's data distribution in Figure 6b exhibits three distinct zones of low, mid, and high temperatures, characterized by varying variances and localizations. In contrast, the Cahn-Hilliard dataset's principal components are depicted in Figure 6c. Four machine learning models are introduced, summarized in Table 1. These include two statistical machine learning methods, GRAD-PCR as a baseline model, and two CNN-based learning approaches. The latter two methods utilize image-specific information, with the CNN method eschewing preprocessed features and the mu-CHA-CNN method indirectly incorporating information from the power spectral density, PSD. This study investigates the application of machine learning models to predict temperatures or energies from microstructure images. Three models are explored: piecewise constant regression, PCR, support vector regression, SVR, and convolutional neural networks, CNN. The PCR model utilizes either gradient-based features or slope and intercept from the power spectral density, with a training process involving binning property data, fitting piecewise constant approximations, and computing mean values. This baseline model, denoted as GRAD-PCR, predicts temperatures or energies by computing the power spectral density, obtaining slope and intercept values, and searching for the nearest point in the learned slope-intercept space. Support vector regression, a statistical learning method, is also employed for regression tasks, particularly suitable for smaller datasets. This model uses either gradient-based features or slope and intercept from the power spectral density, with dimensionless scaling of the data to the range 0, 1, before computing distances. The CNN models leverage image embeddings and principal components analysis for automated feature extraction. These models encompass several CNN architectures and 2 pre-training approaches. The mu-CHA-CNN model, for instance, employs a ResNet34 architecture with a simple training protocol, inputting the image itself, as well as its Fourier and wavelet transformations. This comprehensive overview of machine learning models and features enables a comparative analysis of their performance in predicting temperatures or energies from microstructure images, facilitating the identification of optimal approaches for this task. In this study, support vector machines, SVM, and convolutional neural networks, CNN, were employed to investigate the efficacy of machine learning models in image analysis. The epsilon-insensitive SVM from scikit-learn was utilized, with hyperparameters selected manually or through systematic searches. For CNN, various architectures were explored, including ResNet18, ResNet152, DenseNet121, and EfficientNet-B0. These models were implemented with both pre-trained and random initial weights, and transfer learning was applied to leverage knowledge from existing datasets. The training process involved standardizing the data, early stopping to prevent overfitting, and a learning rate scheduled to optimize model convergence. Additionally, a multi-channel convolutional neural network, MUCHA-CNN, was implemented, comprising residual networks with 34 layers. The input channels consisted of a grayscale image, as well as the magnitude of the fast Fourier transformation and wavelet transformation of the grayscale image. This approach enabled the incorporation of diverse feature representations, enhancing the model's capacity to extract meaningful patterns from the data. This page presents an example of 3-channel images from the Ising and Cahn-Hilliard datasets, with their original, fast Fourier transform, and wavelet transform representations. The training process for a multi-channel CNN involves random initialization of weights, 100 epochs with a fixed learning rate and momentum, stochastic gradient descent as an optimizer, and L1 loss. In the results and discussion section, the performance of different models is assessed using root mean square error, RMSE, and R-squared score on separate testing datasets. The models evaluated include gradient-based physical feature models, support vector regression models with physical features, and convolutional neural network models. The findings indicate that the CNN models, particularly those incorporating physical features, exhibit superior predictive accuracy for both datasets. For the Ising dataset, the CNN models achieve lower RMSE values and higher R-squared scores compared to other approaches, suggesting better prediction capabilities. Similarly, for the Cahn-Hilliard dataset, the CNN models demonstrate improved performance, with significantly lower RMSE values and higher R-squared scores. The table provided summarizes the performance metrics for each model across both datasets, highlighting the effectiveness of the CNN models in predicting phase transitions. Overall, this page illustrates the potential of incorporating physical features into CNN architectures for enhancing the accuracy of phase transition predictions in complex systems. This comparative study evaluates the prediction of microstructure properties using various machine learning models, focusing on the Ising and Cahn-Hilliard datasets. The performance of gradient-based baseline models, support vector regression, SVR, and convolutional neural networks, CNNs, is assessed through root mean squared error, RMSE, values. For the Ising dataset, baseline models exhibit higher RMSE values compared to other models, with the best performing models achieving half the RMSE of the baseline. In contrast, the Cahn-Hilliard dataset shows pronounced differences between models, with the gradient-based baseline model and SVR performing poorly, while the physics-based feature SVR and multi-channel CNN, mu-CHA-CNN, perform best. A detailed analysis of prediction errors is provided through confusion matrices for all models and both datasets. For the Ising dataset, The baseline model exhibits better accuracy for intermediate temperatures but struggles with extreme temperatures. The mu-Chacnn model performs best in the low-temperature regime, although all models face challenges in accurately predicting low-temperature microstructures. In the high-temperature regime, the regular CNN approach outperforms other models. The Cahn-Hilliard dataset analysis reveals that the best models, including the physics-based feature SVR and the mu-Chacnn, exhibit a smaller scatter in their predictions, indicating better performance. The study concludes by highlighting the advantages and disadvantages of each model, as well as identifying limitations and potential avenues for future work. In the low-temperature regime, predicting microstructural patterns is more challenging due to the subtle changes in images resulting from the slowed-down dynamics of the system. In contrast, high-temperature regime predictions are hindered by the increasingly random microstructure and small remnants of the ordered structure. The incorporation of physical features, specifically the power spectral density, PSD, significantly improves low-temperature predictions. The complex SVR model benefits from more complex features, with the Phys-Feat-2 SVR model demonstrating one of the best confusion matrices, achieving balanced performance across all temperatures. Analysis of the Cahn-Hilliard dataset reveals that models trained on this dataset exhibit the worst root mean squared error, RMSE, for the two gradient feature-based methods. This is reflected in the confusion matrix, indicating that simplistic features failed to capture microstructural differences at low energy values and lack generalizability to microstructures from other simulation runs. In contrast, the physical PSD features enable the Phys-Feat-2 SVR model to perform nearly perfectly, with only the mu-Chacnn model performing better due to its utilization of additional image channels obtained from wavelet and Fourier transforms. The CNN, ResNet 18, achieves nearly identical prediction performance, while the CNN PCA-SVR model with 150 principal components performs worse due to its limited feature extraction capabilities. The imbalance of the energy distribution in the dataset contributes to the better RMSE value of CNN PCA-SVR, despite its inferior confusion matrix. The high amount of data for lower energies, where the GRAD PCR and GRAD SVR models perform poorly, also skews the RMSE values. The microstructural patterns in images at low energies are more distinct, leading to better predictions, whereas high-energy regime predictions are less accurate due to the smaller amount of data and larger variance among training examples. The authors investigate the impact of training dataset size on prediction performance and computational requirements for various machine learning models. They compare different models using the Ising and Cahn-Hilliard datasets, focusing on root mean squared error, RMSE, as a measure of accuracy. Figure 9 shows a significant improvement in prediction accuracy when the dataset size increases from 0.1% to 10%, with minor improvements beyond this point. This suggests using at least 10% of the original dataset, approximately 5,000 images, as a good compromise between accuracy and computational efficiency. For small datasets, support vector regression (SVR) methods outperform convolutional neural network (CNN)-based approaches for the Ising model, while for the Cahn-Hilliard model, at least 50 images are required, and only the Phys-Feat-2 SVR method performs well. CNN-based methods show acceptable but less robust performance, dependent on chosen testing samples. The authors also examine the computational and feature engineering effort for each ML approach, as shown in Figure 10. Training and prediction time increase with the size of the training dataset, with the baseline model GRAD PCR being the simplest and fastest to train due to its reliance on binning and averaging of the training data. Computational time for training and prediction in Ising and Cahn-Hilliard datasets, a comparative analysis of PCR, SVR, and CNN models. The computational time required for training and prediction in the Ising and Cahn-Hilliard datasets is a crucial aspect of model selection and optimization. This page delves into the differences in training and prediction times among three models: principal component regression, PCR, support vector regression, SVR, and convolutional neural network, CNN. Principal component regression models exhibit minimal training time, making them an attractive choice for large datasets where computational efficiency is paramount. On the other hand, support vector regression models display exponentially increasing training times with dataset size due to their inherent complexity. This significant increase in computational time can be attributed to the model's ability to handle high-dimensional data and nonlinear relationships, which comes at the cost of computational efficiency. Convolutional neural network models require the most training time, influenced by both model architecture and batch size. The complexity of the neural network architecture, including the number of layers and neurons, directly impacts the computational time. Similarly, the batch size used during training affects the time required for each epoch, with larger batches generally resulting in longer training times but potentially better model performance. This comparative analysis emphasizes the importance of considering computational time in model selection and optimization for large datasets. While models like PCR offer fast training times, they may not capture complex relationships as effectively as SVR or CNN models. Conversely, models with higher computational times, such as SVR and CNN, may provide better predictive accuracy but require substantial computational resources and time. Therefore, researchers must strike a balance between model accuracy and computational efficiency when working with large datasets. The authors discuss the effort required to engineer features for PCR and SVR models, highlighting that while Phys-Feat2 SVR achieves superior prediction accuracy, the identification of physically reasonable features and hyperparameter tuning may outweigh the benefits. Mucha CNN, although requiring no hyperparameter tuning, also demands significant effort. In contrast, shallow CNNs are a good choice when physical features are unclear, but require more training data. CNN PCA-SVR offers a fast-to-train model with acceptable accuracy. The authors emphasize the importance of feature engineering methods, which depend on the nature of the data and require dedicated effort. They investigate the applicability of these approaches to a different dataset from computational fluid dynamics, predicting the Reynolds number from simulated images of fluid flow. While the overall accuracy is slightly lower, Mucha CNN performs better due to its ability to extract important features without relying on engineered features. The conclusion summarizes the investigation of learning and predicting the structure-property relation using various machine learning models, finding that statistical learning approaches with physics-based feature engineering may outperform deep learning-based models in terms of accuracy and trained prediction time. Machine learning models have been shown to reliably predict properties that typically require significant numerical simulation effort, outperforming classical forward simulations. However, these models currently lack generalizability to different domain sizes or boundary conditions, an active area of research across various communities. The authors provide a credit authorship contribution statement, outlining the specific contributions of each author to the software, writing, and formal analysis of the paper. The statement lists the author's roles, including conceptualization, supervision, and funding acquisition. The authors declare no known competing financial interests or personal relationships that could have influenced the work reported in the paper. The paper's data and code are made available at a provided GitLab repository, along with supplementary materials. A permanent DOI is also provided for a snapshot of the repository, ensuring reproducibility and transparency. The authors acknowledge financial support from the European Research Council through the ERC Grant Agreement No. 759419. In Appendix A, the authors provide an explanation of the data generation process using simulation models, highlighting the underlying physical behavior. While the focus of this work is not on simulations, the authors direct readers to relevant sources for further information. The Ising model is a theoretical framework used to describe ferromagnetism, developed by W. Lenz in 1920 and solved for the unidimensional case by E. Ising in 1925. In the two-dimensional scenario, magnetic dipoles are positioned at the center points of an n times n grid. The Hamiltonian, which governs the total energy of the system, is given as H equals J less than I, J greater than sigma I sigma J. In this simplified model, we set H equals 0 and J equals 1 for all magnetic dipoles, resulting in H equals J less than I, J greater than sigma I sigma J. The magnetization of the system, a quantitative measure of the excess dipole signs, is calculated as less than m greater than equals 1, n squared n area summation I sigma I. To simulate this system, the metropolis algorithm is employed. Initially, the n times n dipoles are randomly initialized, with n equals 64 in this case. A site, I, j element of 1, n, is then randomly selected, and the corresponding magnetic dipole is flipped by changing its sign. The energy contribution of the selected site is calculated before and after the flip. If the energy decreases, the flip is accepted; otherwise, it is accepted with a probability given by the Boltzmann factor. This process is repeated for a fixed temperature T, resulting in the final lattice state. In the example provided, the temperature is below the Curie temperature, leading to an organized final state. The authors present a detailed description of their simulation model for magnetic dipole lattices, based on the metropolis algorithm. The model involves randomly selecting a magnetic dipole and proposing a new orientation. If the energy of the new configuration is lower, it is accepted; otherwise, it is accepted with a probability determined by the system's temperature and the energy difference. The critical temperature, or Curie temperature, is calculated as T_C equals 2J K_B, lane 1 plus SQRT 2, approximately 2.269. The simulation stops when each site in the n times n lattice is visited approximately n times, ensuring sufficient time for information to propagate. The Cahn-Hilliard equation is used to describe phase separation in a binary system, including elasticity through a coupling approach between a phase field model and an eigenstrain problem. The composition field, C, evolves according to the minimization of the free energy, E, governed by the equation, partial C, partial T equals m_C, nabla squared, delta E, delta C. The free energy density consists of potential energy density, gradient energy density, and elastic energy density, given by E equals int_ omega, phi_ bulk, plus, phi_ grad, plus, phi_ L. D, omega. The simulation setup for the phase separation process in a binary alloy system utilizes the FENICS library to solve the coupling partial differential equations. The domain size is set at 20 micrometers in both width and height, with elastic stiffness constants C11, C12, and C44 defined as 198 gigapascals, 138 gigapascals, and 97 gigapascals respectively. The density scale C0 is 50 times 10 carat 6 J mu m carat 3, and the gradient energy density Kc is 10 J mu m carat 1. Periodic boundary conditions are applied. The simulation consists of two parts: an initial rapid energy decay phase and a subsequent slow energy decrease phase. For the first part, 2000 steps are run with delta T values spaced evenly on a log scale, ranging from 10 carat 7 s to approximately 10 carat 4 s. In the second part, 10,000 steps are executed with a constant delta T of 10 carat 4 s. Image data is exported at every step of the first part and every 10th step of the second part, resulting in a dataset of roughly 60,000 images. An additional section discusses the hyperparameter search for the support vector regression (SVR) model using phys feet 2 inches features. The SVR model requires three hyperparameters: a regularization term C, a kernel coefficient gamma, and the distance within the epsilon tube epsilon, where points are not penalized. To find optimal values for these hyperparameters, the tree-structured Parson estimator (TPE) is used, followed by handtuning. The TPE search is performed 1024 times, and the model performance is evaluated through 5-fold cross-validation on training data. No test data is seen during the hyperparameter search. The final parameters are provided in Table B.3, revealing characteristic differences between the two datasets. A larger C indicates a stronger penalty for not reaching the epsilon tube region, while a smaller C leads to stronger regularization. The non-uniqueness of predicting temperature from a single snapshot of the simulation trajectory is noted, as the temperature information is related to the probability of flipping the sign of the spin of one of the elementary magnets. This may result in near-identical images at different temperature values. The authors present the hyperparameter settings for the PSDS-VR model in Table B3, which includes the range and logarithmic distribution of parameters, as well as the final parameter values for the Ising and Cahn-Hilliard datasets. To address the non-uniqueness issue in the SVR model, regularization is applied, requiring a higher regularization strength for the Ising dataset compared to the Cahn-Hilliard dataset. The CNN-PCA-SVR approach combines a ResNet-18 with principal component analysis to compute features for support vector regression. This approach is necessary because using only PCA resulted in features that lacked sufficient information, as shown in Figure B.12. The authors then describe how the CNN extracts features, which are then used as input for PCA. The number of principal components is chosen to balance computational cost and prediction performance. Figure B.13 shows the variance explained as a function of the number of principal components, indicating that the variance explained increases rapidly up to 15 principal components, consistent with the decrease in root mean squared error, RMSE, when the number of components is increased from 1 to 15, as shown in the right figure of Figure B13. The support vector regression, SVR, model's performance is evaluated using principal component analysis, PCA, for dimensionality reduction. Figure B.13 shows the cumulative explained variance and root mean squared error, RMSE, as functions of the number of principal components used. The cumulative explained variance increases with each additional component, capturing more data variability, while the RMSE decreases, indicating improved predictive performance. Figure B.14 presents confusion matrices for both datasets with varying principal components, evaluating the model's accuracy and error types. By comparing these matrices, researchers can observe performance changes and identify the optimal number of components. These figures demonstrate the importance of PCA in improving machine learning model performance and highlight the need for careful selection of principal components to avoid overfitting. The paper presents the performance of a model utilizing principal components for image prediction in the Ising and Cahn-Hilliard datasets. In the Ising dataset, the model's ability to differentiate between images in high and low temperature zones is lacking when using one principal component, but it shows improved predictions around the critical temperature. However, with two components, the model's performance significantly improves, similar to Fig. 8. For the Cahn-Hilliard dataset, approximately 25 components are required to achieve similar performance. The model excels at predicting the low-energy regime due to clear patterns, but exhibits error-prone predictions in the mid and high-energy zones. The appendix provides supplementary information on multi-channel CNNs, including Fourier transformations and discrete wavelet transform. The Fourier transform is employed to decompose images into sine and cosine components, with only the magnitude being utilized for image processing. Additionally, the discrete wavelet transform is discussed, focusing on the basic wavelet function. Convolutional neural networks, CNNs, with random initialization and pre-trained weights are compared in terms of prediction performance across varying training set sizes for the Ising and Cahn-Hilliard datasets. In the Ising dataset, both weight initialization methods exhibit similar behavior, with differences emerging only when less than 10% of the training data is utilized, resulting in higher root mean square error, RMSE, values with ImageNet pre-trained weights. The Cahn-Hilliard dataset displays a similar trend, albeit with increased scatter. Notably, training with random model weight initialization yields better performance in both datasets, likely due to differences in image features between the present study and the ImageNet dataset used for pre-training. The small ResNet-18 model achieves the best results for both datasets, consistent with findings that shallow models can outperform complex, deeper models in certain scenarios. Confusion matrices for all models and training dataset sizes are provided in figures C16 and C.17. A comprehensive comparison of the proposed approaches with various regression models from the sklearn library package, including nearest neighbors, linear SVM, RBF-SVM, decision tree, random forest, and neural network, is also presented. This comparison highlights the strengths and limitations of each approach in predicting phase transitions in complex systems. This page presents a comprehensive analysis of the performance of various models on the Ising dataset, focusing on their ability to predict phase transitions as a function of temperature. The primary visualization tool used is the confusion matrix, which provides insight into the predictive capabilities and limitations of each model. The matrices are generated for different sizes of the Ising dataset, allowing for an examination of how the model performances change with varying amounts of training data. The confusion matrices in Figure C.16 span temperatures from 0 to 256, with each subplot representing a different model's performance. The numbers inside each subplot indicate the root mean square error, RMSE, value and the R-squared score, denoted by brackets, respectively. These metrics serve as indicators of the model's accuracy and goodness of fit. A lower RMSE indicates better predictive performance, while an R-squared score closer to 1 suggests that the model explains a large proportion of the variability in the dependent variable. By comparing the RMSE and R-squared scores across different models and dataset sizes, researchers can gain insights into the strengths and weaknesses of each model in capturing the complex phase transitions in the Ising dataset. This analysis can inform the development of more accurate and robust models for predicting phase transitions, ultimately contributing to advancements in understanding and controlling quantum systems. The figure also highlights the importance of dataset size in machine learning model performance. As the size of the dataset increases, the model's predictive capabilities generally improve, reflected in lower RMSE values and higher R-squared scores. This underscores the critical role of data quantity and quality in enhancing model accuracy and reliability. In conclusion, this page offers a detailed examination of the performance of various models on the Ising dataset, shedding light on their strengths and limitations. The use of confusion matrices, RMSE, and R-squared scores provides a comprehensive framework for evaluating the predictive capabilities of these models, ultimately guiding future research directions in quantum machine learning. The figure presents a confusion matrix for various models trained on the Cahn-Hilliard dataset with different sizes. Each subplot displays energy ranges from 0 to 8,000, with the number inside representing the root mean squared error, RMSE, value and the R-squared score. This visual aids in comparing the performance of models across different dataset sizes, providing insights into their accuracy and goodness of fit. The Cahn-Hilliard dataset reveals a competitive performance of the nearest neighbors method, with a root mean squared error, RMSE, of 37 and an R-squared value of 0.996. Closely matching the Phys-Feat-1 PCR approach. This dataset is significant in computational fluid dynamics research. The computational fluid dynamics (CFD) dataset, obtained through large eddy simulations of Kolmogorov flows, presents challenges when learning data for higher Reynolds numbers. This is due to the requirement for higher spatial resolution to capture the complexities at these scales. Visualizations of the proposed approaches applied to this dataset highlight the difficulties in capturing smaller structures at higher Reynolds numbers. These findings underscore the importance of refining algorithms and models to better handle complex fluid dynamics at various scales. The analysis on the 30th page of the research paper presents a comprehensive evaluation of various approaches based on their R-squared score, as visualized in Figure D.19. This figure highlights the comparative performance of different methods, providing insight into their predictive capabilities. Additionally, Figure E.20 showcases the microstructure and corresponding power spectral densities, PSDs, for the computational fluid dynamics, CFD, dataset. This figure aids in understanding the spatial distribution and frequency content of the data, which is crucial for developing effective prediction models. The confusion matrix presented in Figure E.21 provides an assessment of the performance of the proposed approaches on the uniform CFD dataset. Each subplot contains the root mean square error, RMSE, value and the R-squared score, offering a detailed comparison of the model's accuracy and predictive power. The use of R-squared score, RMSE, and confusion matrices demonstrates the author's commitment to rigorous evaluation methodologies, ensuring that the findings are reliable and generalizable. These metrics also facilitate a direct comparison with other studies, allowing for a comprehensive understanding of the state-of-the-art in this field. The author's research builds upon various contributions to deep learning architectures for image classification, including group equivariant convolutional networks and physics-informed neural networks. They reference works on density functional theory, surrogate modeling, and machine learning-based property prediction. Notably, the paper by Bresson et al. 2020 compares different deep learning architectures for chest radiograph classification, while the concept of spinodal decomposition by Cahn, 1961, is highlighted for its significance in materials science. The importance of large-scale image databases, such as ImageNet, Deng et al. 2009, and the role of group equivariant convolutional networks in image classification tasks, Cohen and Welling, 2016, are also acknowledged. Additionally, the authors cite papers on physics-informed neural networks, including Iqbalian et al. 2023, and Espejholt et al. 2022, which present surrogate models and apply deep learning to precipitation forecasts, respectively. The research paper discusses various topics, including deep residual learning for image recognition, computational fluid dynamics, molecular dynamics simulations, the finite element method, Ising's theory of ferromagnetism, protein structure prediction using AlphaFold, and machine learning approaches for structure property linkages and protein ligand binding sites. It references seminal works such as He et al.'s 2016, Deep Residual Learning, Hospital et al.'s 2015, Molecular Dynamics Simulations, Huebner et al.'s 2001, Finite Element Method, Ising's 1925, Theory of Ferromagnetism, Jumper et al.'s 2021, AlphaFold, Jung et al.'s 2019, Machine Learning Approach, and Kandel et al.'s 2021, Protein Ligand Binding Sites Prediction. In the realm of machine learning, material science, and computational modeling, a multitude of studies and methodologies are being explored. One such approach is wavelet analysis, which is facilitated by the Pi-Wavelets package, a Python library utilized in signal processing and image analysis. This technique allows for the decomposition of signals into different frequency components, providing insights into the structure and properties of materials. The study of magnetic phenomena in solid bodies, as initiated by Lenz in 1920, plays a pivotal role in understanding the behavior of materials under various conditions. These phenomena are crucial for the development of new materials with specific properties, such as superconductors or magnets. Computational modeling also plays a significant role in this field, as it enables researchers to simulate the behavior of materials at different scales and under various conditions. This approach can help predict the properties of new materials before they are synthesized, saving time and resources. The integration of machine learning algorithms with material science and computational modeling has opened up new avenues for research. By analyzing large datasets of material properties and behaviors, these algorithms can identify patterns and predict trends, aiding in the discovery of novel materials with desired characteristics. However, despite these advancements, there are still challenges to be addressed. For instance, the complexity of material systems often limits the accuracy of computational models, while the availability and quality of data can impact the reliability of machine learning predictions. Future directions in this field include the development of more sophisticated computational models that can accurately capture the intricate interactions within material systems. Additionally, the creation of large, high-quality datasets will be essential for improving the performance of machine learning algorithms in predicting material properties. Overall, the intersection of machine learning, material science, and computational modeling presents a promising area of research with potential applications in various fields, from energy storage to biomedical devices. As researchers continue to refine their methodologies and overcome existing challenges, we can expect significant advancements in our understanding and manipulation of materials. Deep learning models have been increasingly applied across various fields, including materials science, physics, and biology. The PyTorch library, an imperative-style high-performance deep learning library, has played a significant role in these applications. In materials science, large-scale statistical learning techniques are used for mass transport prediction in porous materials. This involves generating 90,000 artificially generated microstructures, demonstrating the potential of deep learning in predicting complex physical phenomena. Deep hidden physics models are also explored, which learn nonlinear partial differential equations from data. This approach allows for the prediction of complex systems' behavior without explicit knowledge of the underlying physics. Additionally, satellite imagery and deep learning techniques are applied to detect severe convective storms by retrieving vertical profiles of cloud particle effective radius and thermodynamic phase, enhancing accuracy compared to traditional methods. In terms of deformation patterns and surface morphology, a minimal model of amorphous plasticity is discussed. This study utilizes a statistical mechanics approach to understand the behavior of disordered materials under stress. The paper also reviews current progress and open challenges for applying deep learning across the biosciences, emphasizing the importance of addressing issues such as data quality, model interpretability, and the need for domain-specific knowledge in developing effective deep learning models for biological applications. Lastly, the paper concludes with a critical review of multi-physics multi-scale computational frameworks for linking process structure-property relationships in metal additive manufacturing. This framework integrates various computational techniques to simulate the complex interactions between manufacturing processes, material structures, and resulting properties, providing insights into optimizing additive manufacturing processes. Overall, the paper provides a broad overview of deep learning's impact on various fields, showcasing its potential to revolutionize our understanding and prediction of complex phenomena in materials science, physics, and biology. The refined transcript for the explainer video begins here. The research paper presents a comprehensive list of novel methodologies for optimizing data processing in complex systems, focusing on the integration of machine learning algorithms with traditional computational techniques. The authors emphasize the significance of this integration in enhancing system efficiency and accuracy.